As you mentioned, I'm a computer science professor here at the University of Vermont. And what I'd like to do for you all this evening is introduce you to a particular approach to robotics known as evolutionary robotics. But before I show you some evolved robots and we talk about robots in general, if you'll permit me for just 2 minutes, I want to take a couple steps back and talk about some of the global challenges that our society faces. Most of these challenges, not all of them, derive back to a common challenge our society faces, which is how to collect enough energy directly or indirectly from the sun to power our civilization without obviously destroying ourselves or large parts of the planet simultaneously. There are a lot of diverse solutions that we are trying to deploy to gradually decarbonize our energy economy. As you can see just from this small sample on the slide here, there are a lot of diverse solutions out there, but they all share, or most of them share a common feature, which is that regardless of whether we're talking about solar farms, wind farms, tide farms, wave farms, they're all farms. They are all very large collections of large complex machines that are distributed over a very, very large area. The current challenge we face is how to scale up these various farms or swarms of energy collectors so that they could actually make a dent in our collective carbon footprint. There are a lot of challenges to scaling up these technologies. There are legal challenges, labor challenges, environmental challenges. But I would argue one of the major challenges is simply the economic challenge. If we want to build some of these farms on a large enough scale, the cost of deploying the machinery or the infrastructure and maintaining that infrastructure is prohibitive at the moment. It just doesn't make economic sense. Why is maintaining a solar farm or a wind farm or a wave farm so prohibitively expensive? The reason is because all of the construction and maintenance is done by hand. You have a look at any construction site, whether it's building houses, buildings, bridges, roads, wind farms, wave farms. It's all artisanal. It's all done by hand. It's all done by people. And when people are involved, obviously, everything is very expensive. In contrast, if you look at the pair of images in the top of this panel here, the top of this slide, the way in which we build things indoors has been completely revolutionized over the last 100 plus years. In the top left, over 100 years ago, Henry Ford came up with mass production, a way to try and systematize the way that we build things by having the workers be specialized and add a very small part to whatever it is that's being built. And that systematization of the way that we build things indoors was automated many, many decades later, starting in the 1970s with industrial robotics. When you automate the way that you build things, you can build many, many more things much more cost effectively. So we can all own things like this. The bottom pair of images shows that the way in which we build things out of doors hasn't actually changed that much. We used to build things by hand outdoors. We still build things out of doors by hand. If robots are so useful for reducing the cost of building things indoors, why have we not deployed robots at construction sites and other places outdoors to bring down the cost of building things outdoors? The reason, again, there's lots of reasons, but one of the main reasons was actually summarized by the Greek philosopher Heraclitus over 2,000 years ago. Heraclitus was attributed to have said, "Man never enters the same river twice." Humans and organisms, we are masters of adapting whatever it is that we're trying to do as the world around us changes. You've all heard lots of Zoom talks. However, no two Zoom talks are exactly the same. You may be sitting in the same chair, but if we were to zoom into your retina and the muscle fibers in your body, the way you perceive and react to the Zoom talk that you're watching, or when you commute to work each day, from the overall perspective, it looks like you're doing the same thing over and over again, but you're actually confronted by a completely different environment every time. You are never entering the same river twice. If we wanted to deploy robots at a construction site to reduce the cost of building a house or a building or a bridge, Those robots would have to be not only autonomous, they would be making decisions about how to help and what to do on the construction site. They would also have to be adaptive. They would have to adapt to changing light levels, to rain, to snow, to humans coming into close proximity of the machine and then leaving again. Perhaps there's a road bisecting the construction site. The robot is going to have to adapt to pedestrians and cars and traffic and so on. We know how to build complex machines. We can build these things. We can build the International Space Station. We built the James Webb Telescope. We know how to build complex machines. What we do not yet know how to build are autonomous and adaptive machines. However, there is someone who has been building adaptive machines, and she's built trillions and trillions of them, and she's been building them for 3.5 billion years, and she is, of course, Mother Nature. Mother Nature doesn't actually build organisms. She evolves them through Darwinian descent with modification. And if you think about evolution as an algorithm, it is a relatively simple algorithm. Take a collection of things that differ, see how well each of those things does at fitting into its environment, delete or kill off the ones that don't fit their environmental niche very well, and make randomly modified copies of the ones that survive. Rinse and repeat for 3.5 billion years, and at least on this planet, you end up with plants and fungi and fish and amphibians and mammals and us and so on. So in evolutionary robotics, the basic idea is instead of a human roboticist sitting down and building the body and or brain of a robot to try and make it autonomous and adaptive, we as designers take one step back. And instead, we write a computer program known as an evolutionary algorithm or a genetic algorithm. And that evolutionary algorithm will try inside a computer to evolve a virtual robot to do whatever it is that you want that robot to do. Here's a very old example. This is our version of the metaverse here. You're looking at a physics engine, and inside that physics engine, the evolutionary algorithm is gradually evolving robots to, as you can probably guess, grasp and lift this blue object onto the robot's back. I'm showing you a sped up version of this evolutionary process, which took about an hour on a personal computer. Pretty simple process. I'm going to speed up this evolutionary algorithm again and just show you a few points along this evolutionary progression. This evolutionary algorithm actually ran for a full day on this PC. And you can see that not only did these robots evolve to grasp and lift this blue block onto their backs, but every time they evolve to successfully grasp the object, there's a change in the robot's virtual environment. The environment is getting more difficult. The object is being placed further away from the robot, and the robot has to evolve the ability not just to find and grasp and lift and hold on to that object. It's slowly starting to evolve the ability to move from point A to point B to grasp that object. It's a relatively simple robot, relatively simple task. What we did in this case was to ask the evolutionary algorithm to evolve a robot to minimize the distance between that blue object and the gray sensor bulb on its back. We did not tell it to evolve grasping or evolve locomotion. Those things evolved as a side product of what we wanted, which was to minimize the distance from the blue block to the gray bulb. You'll notice in this video that you see some diverse solutions. Not every robot behaves in the same way. You'll notice there's some sort of non-intuitive solutions. This robot tends to move its gripper in synchrony with its legs. It's not quite an efficient way of moving. One of the advantages of an evolutionary algorithm is not necessarily that it optimizes behavior. It produces pretty good behavior and also produces a diversity of behaviors, a diverse set of solutions for us to consider. What actually is this evolutionary algorithm doing? What it is doing is searching over all the possible ways of wiring up the virtual neurons that are inside this robot. So we're searching over the space of all possible brains that this robot could have, and we're searching for that particular brain that causes the robot to lift the object onto its back. Of course, here's a more recent example. This is from a few years back. Here's again us diving into the metaverse. What I'm showing you now is the end result of an evolutionary process after about an hour that's evolved this robot to move from the left side of the table to the right side of the table. In this particular experiment, we took this evolved virtual robot, or this with this evolved brain. We took this evolved brain, took it out of the virtual robot, and dropped it into its physical counterpart. And in this case, the physical robot moves from the left side of its physical table to the right side of its physical table, more or less in the way that its evolved virtual counterpart did. This transferal from simulation to reality is known in robotics as Simtoreal. So typically what we do in evolutionary robotics is evolve populations of virtual robots. Once we have a virtual robot that does what we want it to do, we take part or all of that robot and bring it into reality. We can tell that evolutionary algorithm what the building blocks are that it can play with. In the experiments I've shown you so far, the evolutionary process is playing around with virtual neurons inside the robot, sort of rewiring the brain of the robot. Again, as designers, we can take another step back and allow the evolutionary algorithm to tinker not just with the robot's brain, but with its body as well. In this next experiment, I'm going to show you some robots that are built from different colored cubes. These cubes are soft and can be deformed, as you'll see in a moment. And what the evolutionary algorithm is going to do now is to try and put together different cubes that have different material properties. Some of these cubes are stiffer, some of these cubes are softer. It is sculpting or evolving the body plan of the robot, and it is also evolving the virtual neurons inside. It's co-evolving the body and brain of this virtual robot. You'll notice at this point in the evolutionary process, it's found this 3D shape that produces this slow-moving behavior. And a little bit later in time, the evolutionary process has found this body plan, which allows the robots to move much faster. So we're evolving faster and faster moving virtual robots. And again, we can then try and cross the sim to real gap. We can try and bring some of these evolved robots into reality. Here you see Sam Kriegman, my former graduate student, who's going to present a laser talk in a month's time from now. You can see Sam here taking some hollow cubes. These are built from silicon, a flexible material. And he's putting some air tubes into these cubes so he can inject some air into these cubes and deform them. And this is a snapshot of Sam actually building up a physical version of some of these evolved virtual robots. So I've shown you an evolutionary process that works with neurons and tinkers with ways to connect neurons. I've shown you an evolutionary algorithm that plays with blocks and figures out ways to wire up these blocks. What other kind of building blocks can we make available to an evolutionary algorithm? In this last experiment that I want to introduce you to today, we're going to use, we're still going to allow the evolutionary algorithm to build robots from cubes. I see that someone has raised their hand. So whoever raised their hand, if they want to unmute themselves and ask their question, that's fine with me.
I don't think they can unmute themselves, so they can post a question in the QA.
Okay. All right. We'll tackle your question in the Q&A. So in this last experiment, the evolutionary algorithm is still in the metaverse, in the simulated world. It is going to play with blocks. Those blocks have particular material properties. The blue blocks are going to be soft and passive. They can be pulled and pushed by other blocks. Piero has his hand up. Piero, did you have a question or a comment? No. Okay.
No.
Oh, okay. So blue blocks are soft and passive, and you're going to see red-green blocks that are going to increase and decrease in volume. And unbeknownst to the evolutionary algorithm, these cubes are actually simulated patches of frog tissue. Why would we do such a thing? I'll introduce that idea in a moment. Here are three initial virtual robots made from the blue blocks and these red-green blocks. If you look carefully, you can see the red-green blocks are increasing and decreasing in volume. These are meant to be models of frog heart muscle tissue. Frog heart muscle tissue, like human heart muscle tissue, will spontaneously, those cells or patches of tissue will increase and decrease in volume. And you can see, especially in the top right GIF there, you can see that the passive soft cubes are being pushed and pulled by the active cubes. We told the evolutionary algorithm to evolve combinations of blue and red-green blocks to produce something that moves from the left side of the virtual table to the right side of the virtual table, just like the previous experiment that I showed you. And in this case, this is what the evolutionary process came up with. I'll put this on loop so we can watch this a few times. You'll notice some interesting things about this solution. You'll notice that the red-green voxels are increasing and decreasing in volume, but they're not synchronized. Sometimes one cube will increase in volume while another one is decreasing, and vice versa. So you got a lot of random action or a lot of random components in this virtual robot. Despite this random action, you can see the soft material that has evolved to be on the top half of the robot kind of absorbs all of these random forces and somehow averages or smooths out these forces and guides these forces in a forward direction. So that if we were to trace the trajectory or the movement pattern of this robot, it's moving in a more or less straight line from left to right. Evolution has been able to create a relatively reliable machine that moves reliably, even though it's built from random parts. This is an exceedingly non-intuitive thing for a human engineer to design. These are the kinds of design problems in which an evolutionary algorithm is particularly useful. We took this evolved design and instead of building it from metal or ceramics or plastics or circuitry or sensors or motors, we turned this blueprint over to a microsurgeon, Doug Blackiston. And Doug looked down through a microscope and he took small patches of frog skin cells and small patches of frog heart muscle cells and combine them together to try and produce this 3D form and the right distribution of skin and heart muscle tissue. So he's building up from actual frog cells taken from an early frog embryo, basically from a frog egg, building up a physical version of this virtual robot to make not a robot, but a biobot, or what has become known sort of tongue-in-cheek as a xenobot. The frog that you see at left, this is Xenopus laevis, the African clawed frog. So Xenopus, the frog, becomes Xenobot, the robot. Xeno in Greek also means alien or newcomer. We thought that was also kind of appropriate because this is a very new kind of robot. After Doug had built up this design from frog heart muscle tissues, he produced something that's about 1 millimeter in diameter, so it's just visible to the naked eye. And if he places this small xenobot in the bottom of a petri dish, this physical xenobot moves from left to right, more or less like the its evolved virtual counterpart. So this is a very new application in robotics. These are now biobots. These are robots built completely from biological tissue. And what I've shown you very, very briefly over the last 20 minutes or so is sort of a fast forward through robotics. In the first decades of robotics, we built rigid machines that had jointed appendages like us, built from rigid materials. I showed you soft robots, where now we can build robots that deform their own body to perform certain behaviors. And finally, now we have entered this new era in robotics where we can build robots built purely from biological tissues. What I showed you here is our ability to evolve xenobots that walk. We introduced this work 2 years ago. We published a second paper in this series in March of 2021, where we showed evolved xenobots that could swim. And just last month, we published our third paper in this series where we showed that we could evolve xenobots that self-replicate. I don't have time to go into the details of any of these, although again, Sam Kriegman will be back here to give a laser of his own next month, and he will go into a lot more detail about these xenobots, or otherwise known as computer-designed organisms. So I think I will stop there, and I'm happy to take any questions.